Question is as follows. So, yeah. So, the question is verify whether this is a vector field, vector space. Okay. So, you all can solve the problem. We will wait for 5 minutes and then we can discuss. Yeah. You all try to solve this problem. Then, after 5 minutes, we will discuss the solution. Is it okay? Yeah. Were you all able to solve the problem? Okay. So to show whether this V is a vector space, we need to check whether it is closed under vector addition and scalar multiplication. So if you consider any element X which belongs to V and some other element Y which belongs to V, Then we need to check if it is closed under vector addition. So if you take x plus y, again, this also belongs to V. So this is closed under vector addition. Now we need to check whether it is closed under scalar multiplication. So suppose you consider any alpha which belongs to a real number R, and any element in V which is suppose X that belongs to V, then does alpha into X belong to V? We are supposed to check this. But this doesn't belong to V because it's mentioned that X is greater than 0. And if you take some alpha here which is negative, then it doesn't belong to V. So this question here, this is not a vector space. This V is not a vector space. I hope this is clear. So let's move on to the second question. Uh, so the second question is, suppose consider these vectors which are alpha 1, alpha 2, alpha 3 and alpha 4. Check if these are linearly independent in R4. So I'll give you all 5 minutes. You all can try it out. Then later we can discuss. Yeah, were you all able to solve this problem? Okay, let me solve. So I can rewrite these vectors in matrix form as, okay, as 1 1 2 4, which is alpha 1, and then I can write alpha 2 as 2 minus 1 5 2, 1 alpha 3 is 1 minus 1 minus 4 0, and alpha 4 is 2 1 1 6, right? So to check if these are linearly independent, one of the ways is to check if this matrix formed by these vectors is invertible. So I can reduce this matrix, use row reduced echelon form. So if I reduce this matrix, I'll get, if I multiply R2 by, reduce R2 by considering R2 as 2 minus 2 times R1, then I'll get this as, I'll keep R1 as is, I'll get this as 0 minus 3 minus 9 minus 6. And if I do similarly for R3, if I take R3 as R3 minus R1, I'll get this as 0 minus 2 minus 6 minus 4. And then if I do similarly for R4, I'll get R4 minus 2 R1, which is 0 minus 1 minus 3 minus 2. If I reduce this further, uh, and do some algebraic manipulations, swap some rows and swap these rows, okay, and then if I multiply R2 by minus 1 times R2, I'll get 1 1 2 4 0 1 3 2 0 minus 3 minus 9 minus 6 0 minus 2 minus 6 minus 4, correct? So now if I do, yeah, so if I do some algebraic manipulations again, I'll get the final matrix in the form of 1 1 2 4 0 1 3 2, and then this I'll be getting as 0 0 0 0 0 0 and 0 0. So this basically shows that this matrix is not invertible. So these four vectors which are mentioned in the question are not linearly independent. Is this clear? Okay. So let me move forward to the next question. So the next question is as follows. So you're supposed to find Q1, Q1, Q2, Q3, which are orthonormal vectors from A, B, C, which are columns of A. So this is A, B, and C. Okay, and then you're supposed to do perform QR decomposition on it. Okay, so I'll wait for 5 minutes and then I can solve this. Yeah. Okay, so let me solve this problem. So you can get vector, it's asked to find orthonormal vectors q1, q2 and q3. So you can get q1 directly from column 1, which is a by the length of vector a, correct? So this is nothing but length of vector a, since it's 1 0 0, you'll get it as 1. So this is q1 is nothing but 1 0 0, correct? So q2 will be what? Nothing but the second column is b, so it's b minus projection of vector b on q1. So which is b, yeah, b q1, yeah, times this is projection of vector q1 on b. So this I'm supposed to divide it by the length of vector q2. So that I'll do in the next step. So let me call this as q2 dash. So if you solve for this, you'll get it as, I mean, b is nothing but 203, and b times, I mean, the inner product of dot product of b times q1 is 2. So if you solve this, you'll get it as 0 0 3, correct? So now to get that orthonormal vector q2, you're supposed to divide it by the length of q2 dash, correct? So this is q2, length of q2 dash. So you'll get it as 0 0 1. Is this okay? So now to similarly, you're supposed to find q3 dash, which is nothing but C minus projection of vector q1 on C, so which is C inner product, I mean dot product of C times q1 into q1 minus C times inner product of q2 times q2. So if you solve for this, you'll get it as 0 5 0. So now if you take the, I mean divide it by length of q3 dash, you'll get it as q3 dash divided by length of q3 dash, so which you'll get as 0 1 0. So these are the three orthonormal vectors q1, q2 and q3. So now the next part is they've asked us to find the QR decomposition, right? So I can write it as A is equal to Q times R, where Q is the I mean column vectors which we obtained, which is Q1, Q2 and Q3. So let me rewrite it. So it will be 1 0 0 0 0 1, and this is 0 1 0. Okay. So R is an upper triangular matrix which we obtain as 1 2 4 0 3 6 and 0 0 5. Okay. So I mean, I hope you all understood how we get this matrix R. So this is nothing but the value for A, this is value for B, and this is value for C, which you get by back substitution here. So A you will get directly from the first equation. So which is nothing but A is 1 times q1, right? Because this length is 1. And if you solve similarly, q2 is nothing but, yeah, so this is 3 times q2, correct? This we obtain from this equation. And if I rewrite this, you'll get well equation for b, so which is nothing but this expression here. And then similarly, if you write for c in terms of q3, you'll get this expression here. So this is how I mean, we can decompose a in terms of q and r. So I hope this is clear. Yeah. So yeah, next Chandan will be solving the remaining problems. Okay. Yeah.
Let us look at next example where let V be a vector space for all function f from R to R. Which of the following set of functions are subspace of V, where A is a function f such that f of x square is equal to f of x whole square. B is a function such that f of 0 is equal to f of 1. C is a function such that f of 3 is equal to 1 plus f of minus 5. D is a function such that f of minus 1 is equal to 0, and E is a function which are continuous. So we will wait for 5 minutes and then we can look into the solution.
Hello.
Yes?
Screen is not visible.
Is it visible now?
No, no, not visible.
Like to me, it is visible.
Let us look at the solution. So the question A, the function f such that f of x square is equal to f of x whole square does not form a subspace. Let f of x is equal to x, g of x is equal to x square, then f of x square is equal to f of x whole square, g of x square is equal to x square whole square, which is nothing but g of x whole square. But f plus g of x is equal to x plus x square. F plus g of x square is equal to x square plus x power 4, while f plus g of x whole square is equal to x plus x square whole square, which is nothing but x power 4 plus 2x cube plus x square. Since f plus g of x square is not equal to f plus g of x whole square, the condition does not hold and this is not a subspace. Now let us look at question B. This does form subspace. Here let C be an element in R. Suppose F and G satisfy the property, then C times F plus G of 0 is equal to C times F of 0 plus G of 0, which is equals to F of 1 plus G of 1, which is equals to C F plus G of 1. So thus this function constitute a subspace. Let us look at question C. This does not form a subspace. Here let f of x be a function defined by f of 3 is equal to 1 and f of x is equal to 0 for all x not equal to 3. Let g of x be a function defined by g of minus 5 is equal to 0 and g of x is equal to 1 for all x not equal to 5. Then both f and G satisfy the condition, but F plus G of 3 is equal to F of 3 plus G of 3, which is equals to 1 plus 1, that is 2, while 1 plus F plus G of minus 5, this is equals to 1 plus F of minus 5 plus G of minus 5. This is equals to 1 plus 0 plus 0, that is 1. Since 1 is not equal to 2, F plus G does not satisfy the condition. Now let us look at question D. It does form a subspace. Suppose F and G satisfy the property, and let C be an element in R, then CF plus G of minus 1 is equal to CF of minus 1 plus G of minus 1, that is C of 0 plus 0, which is equals to 0. Thus CF plus G of minus 1 is equal to 0. Therefore, the set of all functions constitute a subspace. And last question, yes, this is also a subspace. Let F and G be a continuous function in R to R, and let C be an element in R. We know that sum and product of continuous function is continuous, and since C is also continuous, it follows that CF plus G is also continuous. And thus set of all such functions constitute a subspace. Now let us look at next question. Here we have to show that a vector A perpendicular to B, if and only if L2 norm of A plus B is equal to square root of L2 norm square of A, L2 norm square of B. And part B, we have to show that non-zero vector A and B make an acute angle if and only if L2 norm of A plus B is greater than square root of L2 norm square of A plus L2 norm square of B. In part C, we have to show that non-zero vector A and B make an obtuse angle if and only if L2 norm of A plus B is less than square root of L2 norm of A square plus L2 norm square of B. We will wait for 5 minutes and then we can look into the solution. let us look at the solution. We can write norm of a plus b square as norm of a square plus 2a transpose b plus norm of b square. We can also write this as norm of a square plus 2 cos theta norm of a into norm of b plus norm of b square. So here it is given that a is perpendicular to b, that is theta is equal to pi by 2. Then cos theta will become 0. Then norm of a plus b is equal to square root of norm of a square plus norm of b square. In part B, it is given that a and b are placed such that they are in acute angle, that is theta is somewhere between 0 to pi by 2. Here cos theta can take values from 1 to 0. If you observe, this is open interval. Then we can write a plus b square as L2 norm of a square plus L2 norm of b square plus 2 cos theta norm of a norm of b. Since cos theta is greater than 0 when theta is equal to 0 to pi by 2, this term will always be greater than norm of a square plus norm of b square. Similarly, when a and b are obtuse angle, the theta will vary between pi by 2 to pi, where cos theta will take values 0 to minus 1. Here, since cos theta takes values between 0 to minus 1, this term will go negative, and hence this will be less than norm of a square plus norm of b square. Let us look at last question. This is a question from the quiz where we have to verify whether trace of AQB forms an inner product or not, where Q is a positive semi-definite matrix. So in order to prove whether trace of AQB forms an inner product or not, we have to verify three properties. So let inner product of AB is equal to trace of AQB. The first property which we should verify is linearity, that is A times A plus B times B inner product with C, we can write this as trace of A times A plus B times B QC, which is equal to trace of A times A QC plus B times B QC. We know that this can be written as trace of A times A Q times C plus trace of B times B into QC. This can further be simplified as A times trace of AQC plus B times trace of BQC, which is equal to A times inner product of AC plus B times inner product of BC. So linearity property satisfies. Similarly, we can show that next property, that is symmetric property, also holds. We can write trace of AQB is equal to trace of BQ, sorry, BAQ. But if we look at third property, that is positive semi-definite property, here the condition that has to be satisfied is trace of Q times A should be greater than or equal to and greater than or equal to 0, and trace of A times QA is equal to 0 if and only if AQ is equal to 0. So we can give a counter example and show that this fails. So for example, let A is equal to 3 minus 4 2 1, and let Q is equal to 0 0 0 1 multiplied by 3 minus 4 2 1, which is nothing but A again. So if we multiply these three matrices, we'll get our final answer as minus 8 minus 4 2 1. Here trace of AQA is equal to minus 1, which is less than 0. So hence this property fails, and thus trace of AQB doesn't form a inner product. Thank you. If you have any questions, you can ask. Otherwise, we can conclude the class at 7 p.m.